Every major database promises the same thing. A reader never blocks a writer never blocks a reader, but each engine keeps its promise in a completely different place. This is where the four versions of MVCC actually live. The promise is multi-version concurrency control. To make a write invisible to old readers, the database doesn't lock, it just keeps a second version of the row. Old readers see the old version, new readers see the new one. The trick is where each database stores that second version, and that single decision cascades into everything: query speed, write performance, and the failure modes that keep DBAs up at night. PostgreSQL is the outlier. It stores every row version directly in the heap. Each row carries a 23-byte header at the front: xmin, the transaction that wrote it, and xmax, the transaction that deleted or updated it. When you run an update, PostgreSQL doesn't really update. It appends a brand new tuple to the heap, sets the new row's xmin to your transaction, and points the old row's ticket forward to the new one. The old tuple stays put, marked invisible to future transactions, but still readable by any transaction that started before your update committed. There's an optimization called heap-only tuples, HOT, that lets update bypass the index when no indexed column changes AU. It just chains the new tuple within the same page AU, but the rule is unchanged. Every version lives in the heap. Eventually, a background process called vacuum walks the heap, finds tuples no future transaction can ever need, and reclaims the space. No other major database needs this step. That's the price PostgreSQL pays for storing every version in place. MySQL's InnoDB takes a different path. Each row carries two hidden fields: a 6-byte transaction ID, dbtrx ID, and a 7-byte roll pointer, db_a_roll ptr. When you update a row, InnoDB writes the new version into the table. The old version goes into a separate structure called the rollback segment, now the undo tablespace since MySQL 8.0. The roll pointer in the new row points back to that old version. When a select needs an older version, InnoDB walks the pointer chain to reconstruct it. A background thread called the purge thread frees undo records that no transaction needs anymore. You can see how it's doing AO. Show engine InnoDB status exposes a counter called the history list length, the number of undo records not yet purged. Above a few thousand, your undo table space is growing. The main table always holds just the latest committed version. No heap load, no vacuum AU, but the undo table space can grow, and a stalled purge thread shows up as a growing history list length. Oracle goes one step further. Every transaction commits at a unique point in time stamped with a system change number, or SCN. The table block carries a small header entry called the interested transaction list, or ITL, which records which transactions have rows locked in this block. When a long-running query needs an older version, Oracle reads the ITL, follows the pointer into the undo segment, and on the fly reconstructs what's called a consistent read clone, a CR clone, of the block at the query's start time. The reconstruction happens in the buffer cache, and the clone lives only for that query. Oracle calls this multi-version read consistency. The trade-off is that long-running reports can fail with ORA 01555, snapshot too old, when the undo retention has been exceeded and the before image has been overwritten. The latest committed row still lives in the block AU, but the version you see can be reconstructed. Microsoft SQL Server takes the cleanest architectural split. The base table holds exactly one version of each row, the latest committed one. When row versioning is enabled through the RCSI option or snapshot isolation, every update copies the prior row into a structure called the version store, which lives in temp database. The base row gets a 14-byte pointer to that version. Readers follow the pointer into temp database to reconstruct older views. This makes temp database a critical resource. A runaway version store can fill temp database and stall the entire instance. Since 2023, SQL Server also ships optimized locking, which uses a transaction ID lock, a TID lock, to reduce lock memory for concurrent writes AU, but the version store mechanic is unchanged. It's a different failure mode, but the same architectural truth. Every engine pays for dead rows somewhere. SQL Server just makes that cost extremely visible by isolating it in its own system database. 4 engines, 4 storage strategies, 1 shared promise. Pick your poison. PostgreSQL's heap bloat and vacuum discipline, InnoDB's undo tablespace and purge thread, Oracle's CR clones and ORA 01555, or SQL Server's version store and temp database pressure, same concurrency guarantee, different maintenance burdens.